Hello everyone and welcome back. Blockchains are really the interesting topic nowadays. We all want to learn more about blockchains mainly because we know our data will be secure. We know that blockchains are immutable and it is very nearly impossible to erase or remove the data that has once been on a blockchain. That's why many companies are actually switching to their supply chains or their transactions on blockchains. The immutability of blockchain actually makes it a global player, and all the companies are trying to make possible and best use of these blockchains and the secure environment that they provide. Before going towards the topic that are blockchains immutable, or is there some way that we can make or erase some data from the blockchains? Let's just understand that what is a blockchain and how, what kind of transactions and how it works in the back end. So first of all, let's take an example of voting web app. Say you selected a candidate you want to vote for and you clicked vote button. This whole event of clicking and the vote button is handled by a web page JavaScript. The code of JavaScript written in HTML and JavaScript is again a transaction that calls for a cast vote function that is somewhere written in a smart contract. So this whole transaction that took place moves over the internet to a local full node. This node is an integral part of a blockchain system. There is not only one but many nodes that are not interrelated to each other. The first node does not know the address of the second node or where it's located or which organization handles that second node, and simultaneously for all. So as in the diagram you can see that the transaction comes from the internet to a local full node, which has a basic function of validating the transaction, means that whether the transaction is valid or not. If it validates the transaction, it propagates that transaction to its peers, also known as peer full nodes. Such and such transaction and validation occurs at the peer node itself until the transaction reaches the mining node. You have to note that full nodes don't have access to the blockchains, or they cannot append any data or validation to the blockchain directly. They just validate your transaction. The addition or append to the block for the valid data happens by the mining nodes only. So when the data moves from mining node at the fifth position, you can see the transaction is placed on a new block and the block is propagated to the peers. So that new block that's created is propagated to the peer full nodes. And while the whole transaction has been validated and the block is validated, executed and propagated to the peers, and there's an event called that the vote has been confirmed, this transaction goes back. Not only the transaction, the result of the transaction goes back through the internet, saying that during block processing, the vote confirmation event is published to subscribed listeners, and through the web page only, we see on the voting web app where we casted the vote first that the vote confirmation is done, the vote has been validated, or thank you for voting. So this goes beyond how nodes actually work in a blockchain and how they are interrelated with each other. Next, coming back to the original topic, whether a blockchain is purely immutable or there is some kind of event where we can erase some data, say in case of some national emergency, right? So I have for you a very interesting paper called Erasing Data from Blockchain Nodes, written by a few very intelligent people in some University of Berlin from Germany. This paper was published in April 2019 and has some really cool proof of concept experiment that has to be heard aloud. So they, in the abstract only, they tell us about that blockchains are immutable, and of course we know that it's technically impossible to erase the data stored on them. But why would we actually want to erase some data on blockchains? So some obvious reasons would be that the data might be illegal, or say it's a pornographic data or some illegal data that needs to be removed. Many organizations nowadays also get forced by the government, especially in EU. There are some laws that force the organizations to keep a track of what data they are handling and if that data is legal or is a harassment or not. So these companies or organizations that hold the data might be compelled by the governments to erase the locally stored data. It can be either encoded on a blockchain or might be stored locally. So, this paper proposes a functionality preserving local erasure. We'll come to that in a bit, but before that, what happens when we actually want to remove some data from a local node? We've already seen a node, but what will happen if we remove some data from that node? So take for example this particular node that we have already seen, say this first local full node. Say if we remove or erase some data from this local full node, and there might be a chance that the incoming transaction has to do something with that data that we erased. That means that this full local node now won't be able to participate in the validation of the incoming transaction because it does not contain that data that is required for the validation. Hence, it comes to this paper which says, in the green it's highlighted, the common assumption for blockchain networks like Bitcoin is that forcing nodes to erase data contained on blockchain is equal to permanently restricting them from participating in the system in a full node role. So it might restrict the nodes from participating as their full node role. So what this paper proposes is FPLE, that stands for functionality preserving local erasure, that actually preserves the functionality of a local node. How we'll be doing this is erasure nodes continue to operate in tune with the network even when erased transaction outputs become relevant for validating subsequent blocks. So since we know that why do we want to remove the data and how it will be done or from where it will be done, let's see the aim of this paper now. It's mainly a proof of concept kind of thing where they want to ensure that the functionality of the local nodes remain intact while we are able to remove some data locally from the nodes. So the FPLE has some pros, that nodes continue to work as before like normal use and they remain in sync with the network. There are no protocol changes and it's compatible with existing UTXO based networks like Bitcoin like networks. It's compatible with that without causing forks or introducing new points of trusts. And also, a local erasure is necessary to figure out whether we'll be able to continue this to a global erasure or not. This tool enables an erasure of transaction outputs from local data stores of Bitcoin core nodes. So, FPLE creates improvement of local pruning. that we'll be understanding in a bit. So let's just check out what kind of data erasure challenges people have faced and how they are trying to solve it, and what all experiments they did to actually provide a solution to this data erasure challenge. So first thing first was to avoid unwanted data. So a easy way of avoiding an unwanted data is have content detectors. That's what we all do, right? It's like a filter. So you filter out the transactions based on the heuristics and knowledge about commonly used data insertion methods, as well as protocol modifications that would greatly increase the cost. So of course it's necessary that if you put so much of restrictions, it would tend to increase the cost of the arbitrary data. And as a Bitcoin, or say this whole blockchain is a global affair, so it's kind of difficult to make sure that to keep everyone on the same page, that they all make sure that these all content filters or content detectors lie on the same page for each and every node and organizations. So it's kind of not possible to be working like that for now. The second technique is redacting the blockchain. So what does redacting means is it's kind of using a chameleon hash functions that enable trusted entities with access to trapdoor key to calculate hash collisions and therefore change published data while maintaining the appearance of chain integrity. So don't be confused. It's basically is that underneath the blockchain would be changed. The data that you want to remove would be changed. But on the top layer would be as similar as before. We'll be maintaining the appearance of the chain integrity. We'll be working as a chameleon that does not becomes the object it stands on, but takes its properties or its colors. That was the second way through for this. The third way through is pruning. So pruning basically means that removing, and it's true for in this case as well. Pruning is widely used technique for locally erasing older parts of blockchain. So pruning was initially introduced when we wanted to set up goals for reducing the storage requirements. It's true, if we have all the data on blockchain, there'll be some time that we won't have enough storage to put things on blockchain. So it might be necessary that we want to erase some older parts of blockchains that don't hinder the transactions occurring right now or in the future. So with FPLE, we'll explicitly consider the erasure of data that is part of UTXO set, the equivalent of state in UTXO based systems. So a pragmatic approach to erasure is in the following. They present a specific proposal towards FPLE, and FPLE enables individual nodes, operators to mark chunk of data for erasure without requiring protocol changes. So how they're doing it at the local level is that the local nodes will be marking chunks of data that require erasure, then do not require any protocol changes and coordination with other nodes or introduction of global trust entities. So we won't be needing any global anchors that need to be taken in trust. We won't be working in coordination with other nodes. There won't be need of coordination, and there won't be requiring of any protocol changes. Hence, everything about erasure would be done locally, right? The basic approach of FPLE is to erase data stored in erasure database. So before coming to erasure database, let's see what kind of outputs require maximum storage. So initially we know that transaction outputs require maximum storage because they have heavily used data. And one of the most challenging when it comes to functionality preserving erasure. So basic approach would be that references to erased data would be stored in the eraser database. Means we are not completely erasing the data, but we will be keeping some references to erased data. So if we need it in the future reference, right? To avoid requesting unwanted data in future, filtering it upon renewed receipt, and being able to differentiate between non-existent and erased data. So think about it that in the transaction itself, there comes a new transaction and you don't know if the data that's coming in is the data that you have already erased and was useless data, or it's some kind of non-existent data that never existed in your database. So to differentiate between that, a erasure database was created where you kept references of the erased data so that we won't confuse the non-existent data with erased data, right? Up next is for dealing with possible validation challenges, we need to employ some principles that whenever validation steps depend on the portion of erased data. So whenever there is need for data, we can surely call up the references. But what about validation? So there are just two things or principles that you need to keep in mind. First one is that nodes ignore and never relay unconfirmed transactions whose validation depends on erased data. So nodes will simply ignore and never relay the unconfirmed transactions. The second one is that if transactions depending on erased data is included on the blockchain, the erasing nodes assume that verification operations related to erased data finished positively. So in essence, for the subset of transactions and blocks for which validation directly depends on the raw erased data, the erasing node assumes a mode of validation akin to the simplified payments verification paradigm. It trusts the miners have sufficiently incentivized to mine a valid block, right? So we're just focusing on a very simple and universally applicable approach. Next is a very basic thing about blockchains, that what are blockchains actually made of. So we all know that blockchains are made of blocks and each block contains a header and a set of transactions we call TX, and block hashes are formed by cryptography and hashing the content of the block headers. These all things just are to inculcate you about what are the transactions and how they are done, what all things actually lie in a block, and what all transactions are done and how they are done. So skipping through this part, let me take you the very interesting part of this erasure transaction parts. So, erasing transaction paths is to desire to erase part of transaction, such as transaction output, arises sometime after the respective transaction has been included on an active chain. Here, data is already stored locally by footnotes when need to erase it arises. So here is a very simple thing that you can understand simply, and let me just show you this erasure of transaction flow chart. So what happens is we have a transaction T and we want to erase some part X from that, and the T transaction has a ID called IT, right? So for that, what we do is we construct a T dash in which X has been already removed. So we store T dash in erasure database with key IT and then physically remove T from the local storage. So that's what's happening is the next time there's a transaction and it asks for T or data from T, the erasure database is checked and T dash is given simply. And how do we validate this erasure with data is that unconfirmed transactions that reference erased data are always considered invalid and are not relayed to other peers. So unconfirmed transactions won't be referenced. And the second one is for confirmed transactions, the SPV heuristics is used for all aspects of transactions that cannot be verified due to previously erased data. That is, it is assumed that if the transaction was included in a block, some miner deemed it to be correct and the transaction is therefore likely to remain part of the consensus. So there are some security implications as well, and here are some diagrams so that you will understand this better. Here is the first diagram. So you have received a transaction T with ID IT. So we'll check first that if IT is in erasure database. If no, then T depends on erased data. So if it does, then T is mined to the chain. And if T does not depend on the erased data, it's validated and store T as usual. If T is mined, so assume T is valid, and if T is not mined, then you just forget about T and don't store it. So this is the basic simple thing that we're trying to do over here in this paper, is that we are not actually trying to remove any data from the original database or from the whole blockchain, the global chain or the global nodes. We are just erasing the data from the local node, but we are keeping a track in the erasure database. We are keeping the track where we erased, and then we are keeping some references for that as well. So whenever there is a transaction coming the way, we can refer to the erasure database. I hope this whole video was interesting and you might want to deep inside and understand more about erasing the data on blockchains. It's to make sure that it's just a proof of concept, and I don't know whether it's being proven or not, but it's a kind of an interesting subject to take upon if you're interested in research. I'll link to this paper in the description and feel free to read it. And thank you so much for joining in, and keep learning.